vertical transformations. We will explore and analyze vertical transformations in quadratic functions. The main one we'll be focused on today is the vertical shift, which occurs when we add or subtract a constant to a squared value. The parent function of a quadratic function is y equals x squared, or also our f of x equals x squared. Every one of our x values, our inputs, are going to be squared, making them all positives from the parent function. Negative 3 squared is positive 9. Negative 2 squared is 4. Negative 1 is 1. 0 is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9, which does give us these locations. On the right for our graph, this is what those points are shown as. And if we were to draw the function in its entirety, that would include the lines. So all the points in between each one of those lines. I wish I could draw a little bit better, but that's the best I got. And our function would look like this graphed. Now, when we are talking about the transformations, we're going to be referring to what it looks like on the graph mainly, as it's the easiest way to represent the change. Now, our transformation form includes 4 different variables that we can change. A, which multiplies our x squared. B, which multiplies our x before it's squared. C, which is added or subtracted before squared. And then what we are focused on today, the D variable, which is added or subtracted after our x is squared. Our example, for starters, is going to be g of x, which is going to be our parent function x squared subtracted by 4. Now in comparison, we've written down our x values at each one of these inputs. And now we calculate what our new function would be, which is going to take the parent function output, the 9, and it subtracts 4 from it. Gives us 5. We subtract 4 from the parent function output 4, which gives us 0. From the output 1, which gives us a negative 3, negative 4, and then it starts going back the opposite direction. Negative 3 goes up to 0 and to 5. So if I were to draw the parent function, or not the parent function, our new function g of x, at an x value negative 3, we would go up to 5. X value of negative 2, we go to 0. Negative 1, we go to negative 3. At an x value of 0, we go down to negative 4. And we start repeating the trend in the opposite direction. 1 is negative 3. 2 is 0. And 3 is our 5. Now, if we finish our function, because there is nothing saying that this is limited, it is continuous. So our new function, g of x, looks as such. Now our parent function's domain was all real numbers. There's nothing limiting what our x value can be. And that's the same for our new g of x function. There's nothing limiting our x values, which means that x, our input, can be all real numbers. It does not matter what number we put in there, we will always have some form of output. But the same cannot be said for range. On our parent function, the lowest value started from the origin, and it was everything above that. So it was y was greater than or equal to 0. Now, because we moved it down, we shifted down 4 units, our lowest value was also shifted down, giving us a range of y values greater than or equal to 4, negative 4. So in this case, the variable d, what is added or subtracted to the squared x, is going to change where our range lowest or highest point is. It shows us where our vertex value is. Another example is if we change the d to a positive number, we add 3 this time. So this is the same as taking our output of the parent function and adding 3 to each one. So if we did the math, that would be negative 2 squared, which would be 4. And then we're adding 3, which gives us the 7. Positive 2, 3. And then we repeat on the other side. 1 squared is 1 plus 3 gives us 4. I just realized I made a mistake on my math. I do apologize for that. Negative 1 squared is a positive 1 plus 3 gives us a 4. This makes a lot more sense. So now we went down to 3. Now we're going back up. So it's always good to check your work as you go on, as I just had to do for my negative 1 input. Now if we were to graph this, at the negative 3 value instead of 9, we go all the way up to 12, which is no longer on my graph. I cannot graph that point. So I moved on to the next one. At negative 2, we have 7, which is on the graph. Negative 1 goes to 4. And 0 goes to 3. Before we change the direction, we go 1 to 4. Location 1, 4. Location 2, 7. And then yet again end up off the graph. This is a continuous function, so we need to show that we're using all values in between each point that we place down. Yet again, there's nothing that is limiting our x values, so we have all real numbers for our domain. Now, unlike the last one where we moved our function downwards, this time we moved it up, changing our range to be greater than or equal to 3. Still, yet again, our range is going to be greater than or equal to our d variable. In this case was a positive 3. So understanding that adding or subtracting a value after everything is done shifts it up or down, we can start looking at equations directly and explaining what they do. Our next section says describe how the graph changes from the parent function f of x equals x squared for each of the functions below. For A, it says g of x is our f of x, our parent function, minus 2. So we can state that this is going to shift because we're adding or subtracting. Because it's negative, we're going down, and the total amount will be 2. Looking at B, where it is a plus 8, we can state that this is going to shift up, because it is positive, we are adding, 8 units. So this is because we are adding or subtracting to our parent function. We affect the output. On a graph, we need to realize that our parent function starts at the origin, so we can make the comparison. In this case, we were only worried about vertical shift. If I look at this, we took our origin and we moved down to a negative 10. So when we move down, we say that as a shift, and we went down 10 units from the origin. And then for D, our last one, we took from the origin and we moved up to 5. So we can say that we shift up 5. So once we have an understanding of what our parent function is supposed to look like, it makes it easier for us to describe any transformations that happen. One of the most basic ones and easy to see is whenever we change by adding or subtracting to the entire equation. When we add or subtract to our squared variable.